From space, this looks simple. It's completely covered in clouds, thick, plain, endless clouds that wrap the entire surface. There are no visible oceans, no continents, no storms you can clearly track. At first glance, it almost looks calm, but that appearance is mistaken, because on this planet, liquid water cannot exist on the surface at all. Instead, nearly all the planet's water is hidden underground, trapped beneath the crust in a massive planet-scale ocean, and the system that keeps it there is both stable and dangerous. Structurally, this planet looks familiar. It has atmosphere, a crust, a mantle, and a core just like Earth, but there's one critical difference. Directly between the crust, there's a continuous global layer of liquid water. Not scattered pockets, not underground lakes, a single connected ocean that wraps around the entire planet. This ocean never reaches the surface, it never evaporates into the atmosphere directly, and it never leaks upward in a meaningful way. Everything about this planet is built to keep the water hidden. The cloud layer on this planet is usually thick, far thicker than Earth's. These clouds trap heat extremely efficiently, creating an intense greenhouse effect. Solar energy enters the atmosphere easily, but once it's inside, it struggles to escape. As a result, surface temperatures are extreme. Any liquid water that reaches the surface instantly evaporates. Rain doesn't pool, rivers can't form, oceans never stabilize. Even though water becomes breezily condenses, it flashes back into vapor almost immediately. From the surface alone, you would conclude this planet is completely dry, and that's exactly why the underground ocean remains hidden. Normally, volcanoes release pressure. Magma rises, gases escape, material is pushed upward and expelled, but on this planet, pressure dramatics are reversed. The atmosphere is so dense and so hot that pressure at the surface is enormous. Meanwhile, under deep, pressure increases even faster due to gravity and depth. The pressure imbalance causes volcanic systems to behave differently. Instead of erupting upward, many volcanic conduits act like intake channels. They don't push material up, they pull material down. Water vapor from the atmosphere is drawn in these openings, condensed by pressure, and transported downward into the subsurface water layer. Over geologic timescales, these processes strips water out of the atmosphere and locks it underground. The planet doesn't lose water, it hides it. At first, this sounds impossible. If the planet is so hot, why does the underground ocean boil away? The answer is pressure. As depth increases, pressure rises dramatically, and the pressure rises the boiling point of water. At the depth of the ocean exists, the pressure is so intense that the water can remain liquid at temperatures far above what would be normally, causing boiling at the surface. At the same time, heat does not move freely upward. The crust acts as a thermal barrier, trapping heat above and insulating the water below. This creates a temperature inversion: hot above, colder below. The result is stable liquid ocean, sealed beneath kilometers of rock, under pressures high enough to prevent explosion and expansion. The water isn't trying to escape, it's trying to equilibrium. The next obvious question is structural. If there's a massive ocean under the crust, why doesn't the crust break apart or sink? Because the pressure is balanced. The weight of the crust pushes it down, the pressure of the water pushes up. Over time, the planet settles into a stable configuration where fractures don't spread, they seal. If a crack forms, water pressure forces materials into it, seals it shut. Instead of a catastrophic collapse, the system self-stabilizes. In a strange way, the underwater ocean helps hold the planet together. For this planet to exist, several conditions must align perfectly. The atmosphere must be thick enough to trap heat. The planet must have enough water to form a global subsurface layer. The crust must be strong enough to contain it, and pressure gradients must favor downward transport instead of eruptions. If any one of these fails, the system collapses. That's why this planet would be extremely rare, but not impossible, and that rarity makes it easy to misclassify. From a distance, this planet looks lifeless. No oceans, no rivers, no obvious signs of habitat. But this most important feature of this planet is completely invisible from orbit. This planet teaches us a dangerous lesson. Surface observations don't tell a full story. Habitat can exist in a place you wouldn't expect, and danger can hide where nothing seems to be happening. Sometimes the most important part of a planet isn't what you see, it's what's buried beneath the surface.